So in this video, I'm going to show how you can solve a differential equation in Python, or more precisely in SymPy. So here we have a differential equation, x prime of t plus 2x of t equals 10 by t plus 2 times the heaviside. This is the heaviside function of t minus 2. This is a fairly simple differential equation, but it turns out that SymPy struggles with solving it. Let's try to solve it in SymPy. So we import SymPy, refer to it as SP. I define t as a symbol, and x as a function. Like that. And then we define the differential equation. I'll define it using the equation operator here. So here we have the derivative of x of t with respect to t plus 2 times x of t equals, so I separate the left hand side from the right hand side using a comma, 10 by t plus 2 multiplied by heavy side of t minus 2, close the bracket. Right, and then we can try to solve it. Solution equals dsolve differential equation. This is the function we're looking for, and I'll use an initial condition, which is x of 0 is equal to 1. And let's look at that solution. Let's run the script. Oh, there's a bracket too much. It's probably up here. Let's just look at it. Something's wrong. This is right. So there's that one is too much. Let's try again. So SymPy takes its time to find a solution to this differential equation. And that's because it's not so easy. There it is. So it does come up with the solution, but as you can see, the solution includes an integral, actually 2 integrals that SymPy hasn't been able to solve. So you get some kind of expression out, but it's really not what we call an explicit solution. So this is not as good as it could be. And the fact is, if I change anything in this, I can easily change this differential equation into something that SymPy can't even find an implicit expression for. So this is an example of something that SymPy just cannot really handle. So what I'll do now is I'll out-comment this part here, and then we'll try to do a numerical solution. And in order to do that, we need to import NumPy, and from SymPy we will import, from SymPy integrate, we will import the ODINT solver. Also, we would like to plot our solution, so I'll import the matplotlib package like that. And the first thing we need to do now is to define the differential equation, and I'll call it dx. And dx, that's my notation for x prime. So what we need to define now is what is x prime equal to? Well, according to this differential equation, it's equal to minus 2x of t plus 10 by t plus 2, heavy side t minus 2. So what I did is I took everything to the right hand side except x prime. So this is what I refer to as dx. As you can see, dx is a function of x itself, and it's a function of t. That it doesn't have to be the case, but it is in this case. So I'll write x and t here. And what this function should return is then minus 2 times x plus 10 divided by t plus 2 times np heavy side. Notice it's the NumPy version of heavy side that I'm using now. T minus 2, and then I need to specify another parameter. I'll choose 1. So what is this parameter? Well, you know that the heaviside function is a function that, let's use another color here. It's a function that's 0 until whatever is inside the function t minus 2, until that becomes 0. And then it jumps to 1 and stays there forever. So I guess in my graph here we have 2 here and 1 here. So the heavy side is 0, and then when the argument t minus 2, when that becomes 0, and it does that when t is 2, then it jumps to 1. But NumPy needs to know what is the value of the function right here. You can see the line is vertical, so what is really the value of the function? And I chose 1. You could have chosen any value between 0 and 1. It doesn't matter, really, but it needs to know. So I chose 1. You can choose 0 or a half or whatever you want. Right, now we've specified the differential equation, then we need to specify the interval in which we want to solve the equation. And I'll go with 0 up to 20, somewhere out here. And I need to specify in what points of time do I want Odient to find a solution for the function. So I'll choose 2, 4, 6, 8, 10, and so on up to 20. That's most easily done by using the command linspace, starting with 0, ending with 20, and then let's use 10 points. That gives me a time series of 0 to, when in fact 11 points would give me 0, 2, 4, 6, up to 20. So that's my time interval. And then I'm ready to do the solution, so I'll write numerical solution. That's what I'll name my solution. And I call the solver odient. That's the name of the command. I need to give the solver the differential equation, dx. So I pass a reference to my function up here. And also I need the starting value of my solution. That's 1, the same as we used up here, right there. And then the time interval that I defined, like that. Now that should be enough. So let's look at the solution. So we'll run the script. Like that. And what you see the output here, let me just open up the window. It starts with 1, and then there's 11 numbers here. Those 11 numbers represent the solution at the time intervals. So let's just try to draw that here. So here we have time. Here we have 0. And we know that the starting point is 1. Let's say that's here. So that's the value of the solution at time 0. So what the solver does is it uses this information, the fact that the time is 0, the fact that the solution is 1, it passes that to the differential equation. So here it's 1, here it's 0. Using those two numbers, the differential equation computes the slope of the solution at this point. Let's mark that by a red tangent, like that. Let's say that slope is probably negative, like that. So that enables the solver to, in a wise manner. This could be done in many different ways, but to find out what would be the value of the solution at the next time step, which is over here, and probably it's something like this, because the slope is pointing this way, so it's probably down here. So this is the next solution point. And at this point, we know what time it is, and we know that the solution is, I don't know, 0.8 or something like that. So those two numbers are then passed again to the differential equation, which in turn computes the slope. So we need to change the color again. And let's say the slope is now like that. And then the solver, using that slope and the fact that we're placed here, computes, and it looks like the next solution point is here. And then we know that the solution is 0.7, so it returns, or it sends 0.7 and the time 4 to find out what's the slope going to be in this at this point. Well, let's say it's like this now. Well, then the solver estimates the next solution point to probably be somewhere up here. And it keeps going like that for as many points as I specified. In my case, 11 points, from 0 to 20. Let's look at the solution. So I'll plot my t points, my t vector. That's my time interval. That's 11 time points against my solution points. Like that. And let's show the plot and run the script. There we are. Now, this curve looks kind of, you can see that, you can actually see the points, that they're connected with straight lines. And that's because we don't really have a lot of points. We only have 11 points. That's not quite enough. So I'll increase the number of points. Let's just go to 100 points. Run the script again. And now the curve looks more smooth. It's still a little jagged down here where the solution changes fast, a little bit up here as well. So I think I'll just increase it to 1,000 points. It's not really a problem. The numerical solution is quite fast. And now it looks very smooth. Down here it's still pointy, but that's because the Heaviside function is an instantaneous function. It acts abruptly. But the rest of the curve is very smooth. So that's as close as we can get to a solution. Notice that this is only a solution for the initial condition x of 0 equals 1. If I want a different initial condition, then I need to make another plot and solve the whole thing again. So I don't get like an analytical expression that I can analyze. I cannot find the complete solution, so to speak, that would require me to make infinitely many plots. I can't do that. So in many ways, I'm very limited with a numerical solution, but sometimes and oftentimes it's the best I can get.